All right. So welcome everyone to this talk in the IQTI Quant Talks seminar series, and it's our great pleasure to invite Professor Giulia Ferrini from Chalmers University to deliver the lecture for today. And Giulia will be talking about quantum computation using continuous variables, which is a very interesting topic. And so a brief bio of Giulia. She is currently an associate professor at the Department of Microtechnology and Nanoscience in Chalmers University of Technology, Gothenburg, Sweden. And she is also a principal investigator at the Wallenberg Center for Quantum Technologies, WACT, which is a Swedish effort to build a quantum computer and researching various aspects of this. And she obtained her PhD from the University of Grenoble in France in 2011, and her thesis was on macroscopic quantum coherence in Bose-Josephson junctions. Then she spent time at Laboratoire Kassler-Brossel in Paris, followed by University Paris Diderot and University of Mainz with a Marie Curie Fellowship. And she is an expert in the area of quantum computation with continuous variables. And at Chalmers, she's an active component in the WACT program, which is a very big grant to research various aspects of quantum technologies. And she is heading the research on quantum computing using continuous variables. So over to Giulia. And before we hand over the stage to her, if you have any question, please raise your hand and I will moderate during the presentation as well as later. Thank you. Over to Giulia. Yeah.
Thank you very much, Bala, for the kind introduction and as well for the invitation. And let me now share my screen. Let's see if I find the presentation. So you now can see the presentation in full screen, right?
No, Giulia. Right now we see a PRL paper.
Well, that's not what it should be. Okay, let me unshare and share again. So desktop. But now do you see the presentation?
Yes. Yes. Yeah.
Okay. Perfect. Okay, so again, thanks for the invitation. We are going to talk about continuous variable quantum computation, and in particular with a focus on resources to achieve quantum advantage in this context. So I will start with an introduction on continuous variable quantum computation, as well as defining what are the typical operations that one needs to be able to perform in this context. And then we are going to talk about how to generate resourceful states and how to implement resourceful gate that can yield to quantum advantage in quantum computing architectures with continuous variables. Then we are going to speak about Bosonic codes, and I will also have a part on how to assess if certain architectures are efficiently classically simulatable, or maybe they provide quantum advantage. And in the end, I will also show how continuous variable system can be a tool to assess the resourcefulness of qubit systems by the use of Bosonic codes. It's a very dense program, but please do interrupt me in case you have questions, and I will try to make my best to make everything as understandable as possible. Okay, so now we start. Usually what do we talk to when we talk about continuous variable quantum computation? Let me first take one step earlier and ask what is quantum computing in general. So typically with two-level systems or qubits, one can consider this as like more standard paradigm of quantum computation that is based on the use of two logical states, 0 and 1, that correspond to the two levels of a quantum mechanical system. And in practice, this can be implemented with any quantum mechanical system like superconducting circuits or light, or trapped ions, or molecules, provided that these systems have two levels that are addressable. So we can control them with some external fields or force. And the key point is that one can consider then superposition of those two levels, alpha 0 plus beta 1, where alpha and beta here are complex parameters that are constrained, so that the square modulus of alpha plus the square modulus of beta is equal to 1. Typically, if you want to implement the most general quantum algorithm, one convenient way of doing that is to use like gates taken by a so-called universal gate set. And here I wrote one of the possible choices. And these are gates that are either single qubit gates, like, for example, the T gate, which is this diagonal gate with this phase on the state 1, and this Hadamard gate, or 4x4 matrices like this control Z gate that is going to induce some entanglement. So there are theorems that show that whichever the quantum algorithm, you can always decompose it in terms of gates from this elementary gate set, which reduces greatly the complexity of designing quantum circuits. But we don't need to resort necessarily to two-level systems for building a quantum computer. We actually can also use continuous variable systems. So the underlying physical model is the quantized harmonic oscillator. And this corresponds to, instead than two levels, to an infinite ladder of levels. Here I represent the first three levels, that correspond to the first three levels of the quantized harmonic oscillator. And this is now described in terms of this Hamiltonian, where A and A dagger are the annihilation and creation operators of a bosonic field. N, expressed as the A dagger A, is the number of photons and basically counts how many excitations there are in each of these levels. And one can also define quadratures, Q like A plus A dagger, and P like A minus A dagger. And these are Hermitian operators, and they have associated observables. And usually, for example, in quantum optics, measuring Q and P means performing homodyne detection. Yes, so why are those systems called continuous variable? The reason is that these quadratures of the field, they have a spectrum that is continuous. So if I write the eigenstate, eigenvalue or eigenvector equations, here represented, the eigenvectors, SQ, are spanned, so they are labeled by a parameter S that is continuous. And they correspond to infinitely energy states that are non-normalizable, so they actually don't exist in the lab, but of course one can always consider the finite energy version of the states, and they perfectly make sense. So to fix the ideas, one can consider the case where this quantized harmonic oscillator is realized by means, for example, of the quantized electromagnetic field. And in this case, Q and P are the real and imaginary part of the complex electric field. Continuous variable systems can be represented conveniently in phase space. And here I plotted, for example, a coherent state. I apologize, this alpha has nothing to do with the alpha of the 2 slides before. Is not at the qubit coefficient alpha. Here it's at a complex parameter, which modulus gives the amplitude of the coherent state, and which phase give the phase of this coherent state. Yes, so why do we want to look into those systems? Recent experiments have showed quite dramatic achievements with continuous variables. In 2016, the group of Akira Furusawa demonstrated the possibility of entangled deterministically 1 million optical modes, and that was not a hard limit. While it's not so easy to entangle such huge number of modes, or like qubits in discrete variable type of systems or qubit systems. Also, the Yale group demonstrated for the first time in 2016 the so-called break-even which means that quantum information encoded in a microwave mode. So they were encoding like qubit type quantum information in a microwave bosonic field. And they were showing that doing so was allowing to have the lifetime of the quantum information living longer with respect to the case of where you don't encode, where you don't do this encoding. And also in 2020, the group of Jiang Pan demonstrated the quantum computational advantage with bosonic system. This was also achieved with qubits by the group of Google and John Martinez at that time. What does it mean, quantum advantage? Usually it means that you want to perform a task like faster than any classical algorithm or computer would be able to do. In particular, we call exponential quantum advantage if your quantum architecture is able to, for example, solve a task in a polynomial time in the size of the circuit, while it will take an exponential time for a classical algorithm to solve the same problem. And here in this quantum advantage demonstration by 2020, the problem addressed, it's a sampling problem. So it's about sampling outcomes of this, the probability distribution that corresponds to this quantum circuit. So it's a little bit of a ad hoc demonstration so far. Same for the Google experiment, but it is still a milestone. And finally, also the group of Xanadu, which actually is a company, put forward a couple of roadmaps for implementing on-chip roadmaps, so on-chip fault-tolerant quantum computers. Also, I wanted to make you notice from this slide, I put in this pink, I underlined that continuous variable from the hardware perspective is a broad topic, because you can actually implement this like a bosonic field either with optical frequencies or microwave frequencies or photonics or even with like the vibrational mode of trapped ions, and there are even many other ways to do that. So in this talk, I will not be focused too much about, not always at least, about the experimental implementation. But sometimes, yes, let's move to this point. Before doing that, so to just have at a glance the differences between what we said so far, we spoke briefly about qubits that are two-level systems. They live on the Bloch sphere, and they are associated to a finite dimensional Hilbert space of dimension 2 for each qubit. And the example of operations for a single qubit are given by this X and Z operation that, as we said before, they are 2 by 2 matrices. While instead for continuous variables, we have a complex plane that allows to represent the state of the field. The associated Hilbert space is infinite dimensional. And then here, if I consider operations like, for example, this P displacement or Q displacement, and if I want to represent them on as a matrix, for example, on the Fock states, then I would get an infinite dimensional matrix. Okay, so now when we want to use quantum hardware for doing continuous variable quantum computing, we have basically two options. The first option is to really use this purely continuous variable aspect of the field, and then use a continuous variable hardware and the software. And in this framework, if I want to implement universal quantum computation, it means that I must be able to approximate any evolution from arbitrary Hamiltonians that are polynomial of the quadratures Q and P to arbitrary precision. This is the definition of what it means doing universal quantum computation in continuous variables. But this is not the only option. I could still use continuous variable hardware, but use it to encode two-level systems like qubits. And I can do this because my continuous variable system has infinitely many levels. So I just need to decide how to restrict my infinite dimensional Hilbert space to accommodate the two levels. So I can do that with a so-called bosonic code. And in this notion, universal quantum computation with a continuous variable hardware means being able to perform the gates from the universal gate set for qubits that I presented before, but where this time they are encoded, supported by a continuous variable hardware. We will come back to both of this notion in the later in the talk. I would like to start with the first family of results and topics that deal with the case that is perfectly a continuous variable, so no encoding. Let's forget about the bosonic codes for the moment. So, so in this case, then, if I want to describe a little bit more in detail what operations one can do to manipulate the state of the field, so we mentioned already displacements where the effect, so they note that they are linear in the quadrature Q, P and Q respectively, and they have the effect of moving the coherent state, for example, or your state you start from in the phase space, like represented here. Also, another important operation is the Fourier transform, which is basically shifting Q to P and P to Q. So basically, it is a 45-degree rigid rotation in phase space. And also, one can consider squeezing and share operations that also are quadratic in the observables Q and P or in Q, and that they basically have the effect of compressing the state. So reducing the fluctuations in one of the two quadratures at the expenses of the fluctuations in the other quadrature. So, and implementing what is called then a squeeze state. And the last important quadratic operation that we see here is this two-mode operation that is called the CZ gate, the continuous variable CZ gate, and it's a two-mode operation that generates entanglement. And as you see here, all of the Hamiltonians that generate these operations are all at most quadratic in the QMP. So as such, they are called Gaussian operations. One convenient way to describe like the state of the field and the operations that we implement on it is provided by phase space representation, and in particular by the Wigner function. The Wigner function is given by this expression, where rho is the density matrix that you consider. And then here we present the state, for example, of the corresponding to the case where this rho is a coherent state or a squeeze state, that both cases have like a positive and Gaussian Wigner function. While in the case of a single photon state, the Wigner function is non-Gaussian and is taking also negative values. And this formalism is actually suitable also to visualize and describe not only states, but also evolutions and measurements by replacing here, instead of rho, either the operator that implements the evolution or the POVM element of the measurement. So the formalism is the same. And now there is an important result that is a theorem saying, it's a no-go theorem, saying that if in a quantum circuit all the elements, so the input state, the gates, and the measurement are all represented by positive Wigner functions, then there is no possible exponential quantum advantage. In other words, it always exists a classical algorithm that allows to simulate efficiently, meaning in a polynomial time, in the size of the circuit, the outcome of the quantum circuit. So this means that if we want to implement some architecture capable of proving quantum advantage, like exponential advantage, like the one that Zhang Weipan showed, then we need to have some Wigner negativity somewhere around in the circuit. Wigner negativity becomes then a necessary condition in order to implement non-trivial quantum computations. And in turn, this also implies that non-Gaussianity is necessary, because Gaussian operations and Gaussian resources in general all have positive Wigner function. So now, if we come back to our notion of universality, we listed before a list of gates that were at most quadratic. They are well Gaussian. So now it appears clear that they cannot be enough to implement universal quantum computation by themselves. But Lloyd and Brownstein in 1999 demonstrated that if one takes at least one non-Gaussian gate, which then is described in this case by a negative Wigner function, then it is sufficient to promote the set of Gaussian operations to universal quantum computation. So now if I write the equivalent of what we had in the first slide for qubits, it was a universal gate set for qubit quantum computation. Now we have a universal gate set for continuous variable quantum computation. We have a displacement, which is linear, a shell, which is quadratic, the Fourier transform also quadratic, the CZ gate quadratic, and finally the cubic phase gate. And one way to implement the cubic phase gate is to prepare a cubic phase state, which is represented by this Wigner function, and it's defined analytically like by applying a cubic phase gate on a squeeze state. And then, so if we have this cubic phase state available and Gaussian operation, then we can implement a cubic phase gate with gate teleportation. And vice versa, if we have a cubic phase gate and the Gaussian operation in states like squeezing, then we can construct a cubic phase state. So the message of this slide is that a cubic operation or state is necessary to promote the Gaussian set of operations to continuous variable universal quantum computation, message number one, and message number two, that the state or the gate, so either the cubic phase state or the cubic phase gate, are two equivalent resources, because if you have one, you can achieve the other one. So now we are going to review three methods that in our group we studied in order to implement a cubic phase gate or a cubic phase state with the microwave setups. Let me mention also that this topic has been researched for a long time with quantum optics, but nobody has ever managed to generate a cubic phase state, neither a cubic phase gate with quantum optic technology, even though this state was suggested 20 years ago. So the first architecture and method that we consider is based on the so-called snail. So the snail stands for superconducting nonlinear asymmetric inductive element, and it was proposed by the Yale group in 2017. It is composed by n small big Josephson junction that are put here in series, and these are put in parallel to a smaller Josephson junction. And all in all, this was summarized by this very cute symbol that stands for a snail, like the acronym says, and indicates the circuit element. So our contribution was to suggest to capacitively couple the snail to a microwave resonator and also endow it with a flux pump, so that the resulting potential, it's a Josephson potential that is a little bit more complex than the one that would stem out of a simple Josephson junction or squid. We still recognize the cosine dependency that is typical of Josephson circuitry, but now the crucial part is that we have the possibility to tailor the potential around its minimum, due to the fact that we can flux modulate both with constant modulation and alternate modulation. And this allows one to really cherry pick the terms of the cosine expansion that one wants and to access to arbitrary nonlinearities. So then my colleagues, in particular Timo Illman, who is actually the person who carried all the calculations of this work, together also with other microwave experts like Fernando, Joran, and Simone, they showed that one can do this expansion of the cosine potential around its minimum, and basically so these terms G of t, they all depend on the modulation, and the message is that for each flux modulation one can really select one of these terms. And in particular, you can select this cubic term and then be able to implement a cubic phase gate natively in this architecture. And you can also use the gate to generate the state, and this is a simulation of how one could combine a squeeze gate and a cubic phase gate by alternatively selecting different terms in this Hamiltonian, first G2 and then G3, and implementing a cubic phase gate. And hopefully experimentalists here will follow this path with based on the snail in the future and demonstrate this proposal experimentally. The second protocol that we studied is also microwave based. And this time we take as a starting point the state that is represented here, and that is called the 3-squeeze state. It was achieved by the group of Chris Wilson in Canada. The idea, what we were asking to ourselves, it was like, okay, this is a non-Gaussian state, but it's not a known resource state that has ever been demonstrated be possible to use to promote Gaussian circuits to universal quantum computation. So our question was, is it possible to find a Gaussian protocol that can convert this 3-squeeze state into a cubic phase state that is known to be a resource state? So then this psi-in is this 3-squeeze state, and then the rest of the circuit is a Gaussian circuit. There is a squeeze state, there is a beam splitter, a displacement, a displacement, a rotation. It doesn't matter too much. You can think about it in terms of Gaussian operations that are tunable. All of these parameters, psi, beta, theta, gamma, and d, they can be tuned. And then we post-select on the we measure homodyne on the first mode, and we post-select on q equal to 0, and we obtain a final state, which is then parameterized by all these parameters. And what we do is that we numerically optimize over all the parameters to maximize the fidelity of the output state with a target cubic phase state. So we do so, and we show that it is indeed possible to obtain a set of parameters such that the output state is with a very high fidelity, corresponding to a cubic phase state with also a quite good success probability. So this kind of corroborates the idea that the 3-squeeze state is itself a resourceful state, because it can be converted to a cubic phase state with a resourceless or Gaussian protocol. And finally, there is a third method that allows to generate a cubic phase gate and a cubic phase state, especially. And this is based on the SNAP. SNAP was also invented by Yale group, and it stands for selective number dependent phase gate, which is this operation that is able then to change the phase of Fox states, applying a different phase to a different Fox state, basically. And the Yale group demonstrated that the SNAP gate, together with displacements, is also universal. And not only it's universal, but it seems to be also very experimentally friendly to implement with microwave circuits. Indeed, one can take a microwave cavity and couple it to a Josephson qubit, and then apply this sequence of displacements and the snaps in order to target arbitrary evolutions. And so this is what has allowed finally Marina Kudra and collaborators at Chalmers, so in our center, to implement the cubic phase state for the first time experimentally. So we are very proud that we achieved the generation of a cubic phase state for the first time in the world using a SNAP-based method. And let me stress again that, so maybe the bottom line message of this slide should be that we really believe that microwave systems are particularly suitable when it comes to generating non-linearities and resource states in continuous variable, in contrast to maybe quantum optics or photonic systems where it is more difficult to achieve these non-linearities. Okay, are there questions so far? maybe it's a good time to take a short question break in case you would like to, before going to the next part, since we changed topics a bit.
So there is one question in the chat box which says, is the continuous variable quantum computing limited to photonic systems, or does it apply to any coherent states formed by matter waves? That was the question.
Any coherent state formed by?
By matter waves.
Matter waves or materials. So well, like I think I don't know if I specified it very well, but the idea is that whichever physical system correspond to a bosonic field, you can use that to implement a continuous variable quantum computer. I mean, a quantum. It should be a quantized, a quantized field, bosonic field. So yeah, you can use really whatever you want. I don't know if I heard correctly, if it was something about matter waves or...
Matter waves, yeah.
Matter waves.
So
I don't know.
I mean, it's a generalized, probably a generalized description of coherent states for... I think you also mentioned about phonons, right? So I think that's...
Okay, then yeah, absolutely. Phonon work. And at Chalmers, there are also groups that study surface acoustic resonators. Well, indeed, it's like the these oscillations in the bulk or the surface of a system that is yielding a bosonic field. So yeah, absolutely, you can also have bulky things.
Okay. Another question again in the chat box is, can you use Kerr nonlinearity to generate cubic phase gates?
Yeah, absolutely. This is precisely what the... okay, I see. Okay, I see. So absolutely, yes. There is a proposal on PRL. I don't have the reference here, but yes, there are proposals published on that. So the answer is absolutely that. Yes.
Okay. I think those were the only two questions, Giulia.
Okay, perfect. Yeah. Then I will resume, and we go now to bosonic codes. So what does it mean to use or to have a bosonic code? The idea is that we want to implement to encode a qubit state into an oscillator. We said before that in principle we can do that because qubits are identified by 2 levels and oscillators by infinitely many. So it's just about picking up which levels are going to define our oscillator. And indeed, in practice, any 2 orthogonal wave functions can encode a qubit. The simplest example one can think about is identifying the 0 logical state of the qubit with the photon state 0, so where we have vacuum, there are no photons, and the first, so the state 1 of the qubit with the single photon state, n equal to 1. An alternative is to use 2 coherent states of opposite phase, so they are not exactly orthogonal like 0 and 1 should be, but they are quasi-orthogonal in the case where the amplitude is sufficiently large. So they can also serve the purpose. However, not all these encodings are good if you want to implement error correcting code. For example, if now you consider the case where there are photon losses, and you take this first encoding that we choose, then if you lose a photon, then your state 1 will immediately collapse into 0. So it will immediately, collapse is not the right word, but it will immediately be brought to 0. And then all your quantum information is lost because you translate 1 photon loss into a bit flip. So the idea of bosonic codes is to find this superposition of Fock states, for example, in a little bit more clever way, so that they can protect against some noise or loss event, for example. So a minimal extension of the code that we had in the previous slide is this binomial state, or binomial kitten, as referred to in this review on bosonic codes that I will highly recommend. It is very clear and pedagogical. So here we identify the state 0 with the superposition 0 photons plus 4 photons. and then the state 1 with the state n equal to 2, the Fock state n equal to 2. And these two states are represented, so their Wigner function is represented here. You see that the photon, like n equal to 2, or so the encoded state n equal 1, has this rotational symmetry, and this 0 has this discrete rotational symmetry. And with this, I can define my qubit. And now, if there is a loss event, then what happens is that if the loss applies to this state, so this 0 term goes away, and this 4 becomes 3, while this 2 becomes 1. So if I start from alpha 0 plus beta 1 and I have a loss event, I will find myself with alpha 3 plus beta 1. And now this has a different parity. You can see that this qubit lives in a subspace of the Hilbert space that has an even parity, while after one loss event occurs, the state is brought out of the computational subspace into a space that has odd parity. Therefore, with parity measurement, one can detect if an error has occurred, and in that case, one can design an error recovery, so a state recovery procedure, where one is able then to bring back the state to the original encoded qubit, living in our even parity computational subspace. So this is the potential of bosonic codes for quantum error correction. So this binomial kitten that I represented there is one out of many possible codes that have rotational symmetry, identified by a certain parameter n that gives the degree of the symmetry. In this slide, n is equal to 4 for all the possible examples. And there is a variety of such rotationally symmetric bosonic codes. You can also see by the analytical expression that they are defined like a certain primitive. This theta is different things depending on the code. So it's a coherent state here, a squeezed state here, like some blob here, and an infinitely squeezed state here. And then you apply this rotation that replicates your primitive an amount of times that depends on the order of the symmetry. These codes were systematized by Arne Grinsmo et al. In this paper, and they were also implemented experimentally in different groups, Yale, Tsinghua, and also Chalmers, while like proof of principle error correction so far was only achieved at Yale and Tsinghua universities. So then what we studied with theorists, theory groups, collaborators, and in particular, let me again stress that Timur Yilman carried out the integrality of the analysis in this paper. So we were studying the performance of these rotationally symmetric bosonic codes when the recovery procedure happens under realistic conditions, and in particular in the case where to decode here, you need to do a phase measurement to discriminate, for example, if you have this blue dot or the red dot. And this phase measurement that is usually modeled through a canonical, so it's described by a canonical operator that doesn't correspond really to anything physically. So what Timo did was to really design a protocol that entails physical implementation of this phase measurement, such as the heterodyne detection or the adaptive homodyne detection, and also allow for this detection not to be perfect. So he also considered some detection inefficiencies. And it showed that for relevant parameters of the detection efficiencies or inefficiencies, it is still possible for the code, the rotational symmetric bosonic codes to break even. It means that it's still, so this line is this break-even point, like I introduced in the beginning of the talk. That is the line that separates when it makes sense to perform a quantum error correction, which is the white area, from the shaded area. where the infidelity 1 minus f becomes above the level where it's basically better not to do the encoding. So yeah, this work was corroborating the robustness of rotationally symmetric bosonic codes in the presence of realistic state recovery conditions. But rotationally symmetric bosonic codes are not the only way how you can implement a bosonic code. Indeed, you can also consider translationally symmetric bosonic codes or GKP codes by Gottesman, Kitaev, and Preskill, who first introduced those states. And those are invariant by translation of 2 square root of pi. So now what is represented here is the wave function in the position representation. So you see that this is the 0 logical state, and it's a train of delta functions that are placed at even multiples of square root of pi. We have 2 square root of pi, 4 square root of pi, etc. And then we have the 1 logical state where the peaks are placed at even multiples. And obviously those 2 states are orthogonal. And so far they were implemented, okay, not those which are infinite energy, but their finite energy realization was achieved at ETH with trapped ions and Yale at Chalmers with microwave systems. And in this bosonic code, in this GKP code, is actually interesting and quite easy to understand what are the encoded operations. It means, suppose that you want to implement the X gate that flips your qubit from 0 to 1. Then what is the continuous variable operation that is going to implement this? It's actually quite easy to be convinced that it is this displacement that we introduced before by square root of pi. Because this is going to introduce a shift in the position direction. And then if I shift my blue comb by square root of pi, the spikes will align with the red comb. And then it means that I shifted from 0 to 1. And similarly, one can also define can also calculate what are the other logical operations encoded in continuous variables. So the Hadamard corresponds to the Fourier transform, the S phase gate corresponds to the share, and the continuous variable Z implements the discrete variable Z. So GKP states are quite nice because they really yield a very fine correspondence between continuous variable and qubit operations. Now, since we spoke about the second notion of universality using the continuous variable hardware, let me refresh what this is and let's look at it in the context of GKP codes. So we said that universality with bosonic codes means the ability to implement the universal gate set of qubit operation on the encoded qubit, so on the continuous variable hardware. So, and with the GKP code, the Hadamard we said is implemented by the Fourier transform. The control not is implemented by the CZ gate in continuous variable. And the T is implemented by this cubic phase gate, modulo some correction here. You have some Gaussian correction. So basically, the T gate for GKP states encoded in continuous variable is implemented by the cubic phase states modulo some correction. And one thing that I would like you to also notice is that so those GKP states that have this grid structure, we look at them before in the position representation, but we can also look at them at the Wigner function, and they're identified by peaks. So it's a grid of peaks that are positive or negative. 1/4 of the summands are negative and 3/4 are positive. So the positives are these clear dots. And and then also I wanted to mention that Laura calculated. So this is the expression. These are the plots for the 0 and 1 states, and then Laura generalized this to arbitrarily encoded the states in this paper. But then one point that I wanted to make is that these GKP states encoded in continuous variable, even the 0 and the 1, they do have a highly negative Wigner function. So then we saw before that Wigner function is a resource for quantum advantage. So one question that one could ask is this enough to supply Gaussian circuits with quantum advantage, no matter what the Gaussian circuit is, no matter what the Gaussian operations we take? Yes. So basically, we are thinking about mixing somehow continuous variable resources, meaning the negativity of this Wigner function of the GKP states, and with Gaussian circuits, and see if this can always bring to quantum advantage for continuous variable quantum computation, or if there are cases where this is going to be classically efficiently simulatable. So with this, I can go to the following topic. So maybe again, if there are questions on this part, it's good to ask now, maybe. Of course, we can take more questions later.
So I have a question, actually, from my side. So you showed the encoding in terms of the binomial kitten states, right?
Yeah.
So is there, I mean, I found the choice of the logical 0 and the choice of 1 rather curious thing, where the energy, the average energy of the 0 state is actually more than that of the 1 state. Is there any?
Yeah, there is a discussion on this point, Bala. I think it's exactly in this paper there is an extensive discussion on this.
Okay.
There are consequences. What you say has consequences, and it's also possible to do the other choice where instead you calibrate such that your 0 logical and 1 logical have the same average energy. I cannot remember exactly the content of the discussion, but in this review, this is extensively discussed.
Okay, I'll take a look. Thanks.
Yeah.
Any other questions? Okay, we can probably move forward and wait for questions at the end. Yeah.
Okay, perfect. Okay, so then we go to this other part of the talk where we want to assess if certain Gaussian circuits with input GKP states are classically efficiently simulatable, or they can provide quantum advantage. So we first we had this question, like, is it always enough to plug GKP states, and just because it's Wigner negative, we plug it to a Gaussian circuit and it will provide advantage? Is it true or false? Actually, we can reply to this question very simply, with not a big deal of calculations, by just taking a look at this qubit theorem. It's called the Gottesman-Neal theorem, and it's somehow the equivalent of Mari-Isert for the qubits. So if you take an architecture based on qubits that is initializing Pauli eigenstates, and then you only apply Clifford operations. Clifford operations are those generated by H and S and the C0. So there is no T-gate, basically. And what they do is that they only move Pauli states to Pauli states. So basically one moves from one vertex of this octaedron to another vertex of this octaedron, never populating or exploring other parts of the Bloch sphere, and when we do Pauli measurements. And the Gottesman-Neal theorem says that it is always possible to provide a classical algorithm to simulate efficiently these types of architectures with a classical computer. Yes. So then we can basically take this result and provide immediately a counterexample that will disprove our question before, and will show that no, it's not true that no matter how we place our GKP states, then we can always obtain quantum advantage. So what one can do is that we can construct this trivial counterexample where we take really the hypothesis of the Gottesman-Mill theorem. So we put our GKP qubits into a Pauli eigenstate, for example, 0. The 2 stands for qubits here. Then we apply only Clifford operation. We mentioned before H, S, and CZ. And then we also implement, okay, homodyne detection corresponds to measuring in the computational basis 0 and 1. So basically, this is really like transferring the Gottesman-Mill theorem into an encoded GKP architecture. And then this circuit is trivially simulatable efficiently due to the Gottesman-Mill theorem for qubits, even if the GKP qubits have a highly negative Wigner function. So basically, it's an example on how to make a bad use of a resource somehow. So by itself is not a very surprise statement. But what we realized is that when instead one consider displacements that do not correspond to something that has any equivalence in the qubit subspace. So before, sorry, let me take a step back. So here we also allow for displacements that like X that takes 0 to 1, like we saw before. We spoke before about the fact that this displacement by square root of 2 pi brings one comb to the other comb, so implements the gate X. And this gate Z is also another square root of pi displacement in Q. So these basically continue to map the qubit onto the computational subspace. But if you take now GKP encoded qubits with Clifford operations plus those displacements that are now, ISIS can be a parameter that can be much smaller than square root of pi, for example. It can be an arbitrary fraction of square root of pi. So it means that now this doesn't correspond anymore to anything in the computational subspace of the qubit. So then it's really an open question whether this architecture is classically efficiently simulatable or if it is hard to sample. And in particular, this cannot be assessed trivially with the Gottesman-Mill theorem because these displacements bring the GKP qubit out of the computational subspace. And in the same time, we cannot apply the Mari-Eiser theorem that would say that continuous variable architectures with all positive Wigner functions are simulatable because the input states are GKP states that have a negative Wigner function. So this we really argue that is a non-trivial question. And Laura was able to show, together with Cameron and Alessandro and myself, to show that in the case where this parameter identifying the displacement is an arbitrary fraction of square root of pi, then these circuits indeed are classically efficiently simulatable. And she did that by mapping the qubits into higher dimensional qubits and by interpreting those displacements as this like Clifford qubit operation in a higher dimensional subspace. We will not go into the detail of the demonstration. I just wanted to make a last point, and it is that although what we show here is that it is not true that by itself the Wigner negativity of a GKP state would be always sufficient to promote Gaussian operations to like something that yields to quantum advantage. It is actually possible in different ways to restore quantum advantage by taking combinations of GKP qubits and Gaussian circuits, and there are at least 2 ways. One way is to take T states instead than to encode the T states, so other states than 0, states that are not Pauli eigenstates, and these have been shown to yield hard to sample circuits, so quantum advantage. And the other case is to to consider other Gaussian elements that are not these Gaussian operations that are written here. But I will not go into more further technical details on this. I think I am ready to go to the last part of the talk.
So yeah, so you do have about 10 minutes, so not a problem.
Oh, it's perfect.
Yeah.
Okay, good. So this is the last section, and here we are going to close the circle and come back to qubits. And we want to assess the resourcefulness now of qubit states, but using a continuous variable mapping through the bosonic encoding. So we care about magic states. What are magic states? We mentioned before the Gottesman-Lil theorem, and we said that Pauli eigenstates together with Clifford operations, they are always simulatable. So magic states are such states that allow for promoting Clifford operations and Pauli measurement to universal quantum computation. So they are states that are out of the hypothesis of the Gottesman-Lil theorem. Examples of these states are the T state and the H state. So the H state lies here on the equator of the Bloch sphere at 45 degrees between plus and I, eigenstates of X and Y respectively, and the T state lies somewhere around here where this yellow dot is. And they are resourceful because we saw that in the Gottesman-Lil theorem there are only the Clifford operations that are there. If you have a T state or an H state, then you can always implement, you can also implement the T gate, which was missing to the set before to have universal qubit quantum computation. So this is a little bit the same concept that we saw before, that a cubic phase state and a cubic phase gate are equivalent resources, and here for qubits is the same. T magic state or a H magic state and a T magic gate or a gate are equivalent resources. And if you have one, you can implement the other one by gate teleportation with resourceless operations. So then people in the qubit literature, they have really spent a lot of time and effort to quantify how magic is a state. And this is usually done by magic measures that are functionals over the Hilbert space that satisfy certain property. For example, you want that the magic measure of a state that is no magic is equal to 0. For example, Pauli eigenstates are not magic. We want that the magic measures of Pauli eigenstates to be equal to 0. However, typical such magic measures are difficult to compute. And so one question is, can we find a new magic measure that it's easier to calculate for larger qubit systems? So far, 5 qubit is kind of the limit. We would like to go beyond. And our idea was to use the GKP encoding in order to map a qubit into the continuous variable system, then calculate the amount of Wigner negativity of the encoded state, and see if that can be used as a magic measure. Yeah, we saw before that the Wigner function of GKP states is characterized by this grid of peaks, so it is periodic because GKP states are this are translational invariant. So one can identify a cell of size square root of pi. Or maybe someone has unmuted accidentally.
Yeah. I muted the participant. No problem. Carry on, okay. Please.
It's okay. Yeah. So what I wanted to say is that we can restrict it to one grid. We don't need to look at the full phase space. We can look at the Wigner function in one grid. And what we did was to compute the Wigner function. So the negativity of the volume of the negative region of the Wigner function in one cell for each encoded qubits in the Bloch sphere. So you take a point in the Bloch sphere. it's parameterized by a certain theta and phi. You, with the GKP encoding, you write down the GKP state. Then you write its Wigner function, and then you compute the volume of the negative region. And this is what gives rise to this table. And what we noticed is that this Pauli eigenstate, they always have the same value of the Wigner negativity, while the H and the T, which are magic, they have a higher value. So that's why really we had the idea of using the volume of the negative region of the Wigner function of encoded GKP states as a measure of magic for qubits. Yeah, this is exactly where the idea came from. And then we just followed this program, and we considered arbitrary pure qubit states identified by these CI coefficients for n qubit. And then we computed after GKP encoding the volume of the negative region. And then Lina and Oliver, together with the supervision of Laura and myself and Alessandro, were able to show that in the end, when you do this, you can, we were also taking off the offset value corresponding to the volume of the negative region of Pauli eigenstates or stabilizer states encoded with GKP states. And then we arrived to this very compact expression where all the continuous variable structure has somehow disappeared, but it is what has allowed us to achieve this result. And indeed, at the end, we call this GKP magic, and it is our magic measure. And Oliver then proved that it is equivalent to the ST norm that was defined before, not as a magic measure, but as a magic witness, where there are some subtleties regarding which properties are satisfied in the definition. And then one striking point is that our GKP magic is now able to, is possible to compute for a larger system of qubits, up to 12 qubits on a laptop in some minutes. And this is not a hard limit, therefore. So it is easier to compute than previously defined magic measures. And yes, so this is the end of the talk. I can conclude. We saw different things. We started by speaking about how to generate resource states and how to implement resourceful gates in microwave systems. And I was proud to show you the results from Marina Kudra, where she was able to implement the first cubic phase state. Then I also introduced Bosonic codes and told you that rotational symmetric Bosonic codes were shown to be robust when there is noise in the recovery operations, and they still yield the break-even potential. Then we assessed that not always GKP states or even Wigner negative states supply quantum advantage to Gaussian circuits. Sometimes they do, but sometimes not. We were able to prove that some circuits for which it's non-trivial to assess the simulatability are actually classically efficiently simulatable. And finally, in the last part, I told you how it is possible to use the GKP mapping in order to define a magic measure for qubits that is easier to compute than what was previously possible. And with this, I would like to thank all my collaborators for the nice time working together, as well as for you for your attention. Thank you very much.
Thank you, Giulia, for a very comprehensive and wonderful talk. And let us thank the speaker first. And let us then have questions. Yeah, Apurva, please unmute and you can ask the question.
For the cubic state or the cubic phase, you wrote down a Hamiltonian where there was a term A plus A dagger, the whole thing cubed. Now this Hamiltonian is not bounded from below. So does it cause any problem? Or you are using some truncated analysis?
It's a very good question. It's a very good question. Yes, in principle, it can cause problems, but we always restrict certain Fock space dimensions where these are not manifest. And once again, there are discussions on this. Maybe I could, there are a couple of papers, maybe I could email you those directly where this has been assessed. We don't, I mean, you know, in practice, then in the laboratory, like there will be energy scales, and at the energy scales where we work or where we simulate the generation of our cubic phase state, there are no problems, and we have reasons to believe that the model is, we really even performed some more ab initio simulations, and we know that the approximations that we made to arrive at that Hamiltonian are reliable. To the energy scale at which we perform the simulations, and that are also those at which experiments are sensible to make in the labs. So from an experimental perspective, these Hamiltonian and plots that I showed describe quantitatively what we do expect to see in the lab when people will do the experiment. Then in principle, I agree with you that there can be a problem with that, but not at the energy scales where we looked at.
So is it similar to using just the cubic term in a perturbative expansion?
Sorry, is it similar to use just a cubic term?
As a perturbative expansion, not a complete solution. Perturbation theory.
I'm not. I don't hear you very well, actually.
So he's asking if it is similar to using the cubic term as in perturbation theory in the expansion. Yeah.
I would say so.
So, Apurva?
No, that's all.
Okay. Okay. Yeah. Thanks, Apurva. So any further questions from other members of the audience? Okay, so I have a question while, yeah. So then from what I understand, so the break even has been demonstrated so far only in the bosonic encoded qubits, right? Is that my understanding correct? And what is the role of, you know, what is the status of error correction in the other strategies that you discussed, Giulia?
So in the other strategies for, so yes, for the moment,
continuous variable, yeah.
Yeah, for example, trapped ions and these kind of things. So it's another very good question because the break even is also a lot about how one defines it. So for the moment, they defined the people in Yale. They were defining it corresponding. So like if you would take like was it just a moment. So basically, so it was corresponding to the case where you have an unencoded qubit, where you consider like a single photon in the cavity. That is then your like state 1, so to say, and then you let it go through the same noise channel that you would have if like where are you? Sorry, yeah, that you would have that your code encoded qubit going through. Yeah, so this is the definition that they took, but this is also very much depending on you know, the quality of the cavity that you use to do this. So one can a little bit artificially, by having a relatively bad cavity, you can artificially have your lifetime of the unencoded qubit be low, and then you do the encoding and it works a little bit better. So in this sense, it's a little bit arbitrary. And I was asking exactly the same question that you asked to Jonathan Combe when he was presenting his experimental result on GKP on trapped ions. I was asking him the same. I asked him, okay, but does it mean that you had break even? And he was saying, well, break even depends on how you define it. So he was not playing this game somehow. He was not forcing, some definition of unencoded qubit. So it's a little bit ambiguous, I would say.
All right. Okay, then I have a very general question, meaning, so what is the general class of problems where continuous variable computation has an advantage over discrete variables? Is there a general class of problems where this distinguishes itself from discrete variables, or do they span the same space of problems?
I think we don't know yet. One, in terms of you ask about problems, and it's a fair question. But if we speak about the computational models, for example, we know that optical modes are very good to generate, like you said, large cluster states that are good to do measurement-based quantum computation. So that seems to be quite native to quantum optics, for example. Otherwise, okay, we have this boson sampler or this quantum advantage type of chips, and then, okay, you can also do those with qubits. So it's still a little bit unclear. I would say I had this slide with those that, in my opinion, are some among the most striking points in favor of continuous variables, and it was this deterministic generation of super large entangled state, which has no qubit equivalent, and then this possibility of encoding the lifetime, so of encoding qubits into bosonic codes and then extend the lifetime. Now there was this, ambiguous definition of break-even, but suppose that you can really push this very far and then demonstrated unambiguously that really bosonic code preserve the lifetime of quantum information, because you can then perform the active error correction also. So I think, I think it's a very promising avenue, and I do this because I like it. But as the same thing as for the technology, that there are microwave and the ions and the atoms, etc. There is not one only device to stick to, and I think with the software part is the same, that we should still be a little bit open, and it's still unclear what will be the best approach, I guess.
Absolutely, all of us are in the same boat. Yes. Any other questions from the audience?
Bala, there are 2 questions in the chat box.
The chat. Okay, let me just read them out. Okay, so I think I read the first 2 questions. The second question that we have from Shri Ganapati is, why are GKP states difficult to prepare experimentally? Is it due to the fact that they are a series of delta functions and we approximate them by a series of Gaussian pulses or peaks?
Yeah. So retrospectively, with the microwave, they were not so difficult because, or with the trapped ions, it was possible. They are difficult to implement optically because they are highly non-Gaussian. They have this very complex structure, and typically what people do with quantum optics, they can subtract a photon or add a photon, or they can maybe have a, the nonlinear crystal will still have some squeezing effect, but not maybe non-Gaussian effect. So I would say that they are difficult in quantum optics because there are few non-linearities, but retrospectively they were not super. I mean, people managed to do them in 3 different groups with microwaves, and they will probably become routinely produced.
So I have a related, so it is interesting that you bring in the advantage that the microwave regime has for such. It is also true that in the microwave regime, you do have the ability to generate both chi2 and chi3 non-linearities, right? So, which is, and you can do that with fair amount of ease. So does this also give an advantage, or is it just the strength of the non-linearity which matters in this case?
I think
can something interesting be done both in the 3-wave and 4-wave mixing cases, or?
I think it's similarly as to the question that someone asked before about the Kerr non-linearity. So similarly to that, you can use all, you have a lot of knobs to tweak non-linearities, and from a purely theoretical perspective, all what you want is to have this universal gate set of operations, for example. Or you can also forget about that and discover a new one, like the snapshot people did, that changed the rule of the games and came out with a different set of gates that are universal. So I think whichever creative way you want to find to tweak your nonlinearities, you can definitely do that, and there is abundance of them, as you say, in the microwave systems. I think Timo, my collaborator, also has another paper with Fernando on another method to generate. I wonder if it is replying to your question more specifically. Maybe I can take a quick look. Yeah. Let's see. So this was about designing Kerr interactions for quantum information processing via counter-rotating terms of asymmetric Josephson junction loops. Okay, this was Kerr still higher order than.
Okay. Okay, I'll take a look. Okay, any other questions? If there are no other questions, probably we can then thank the speaker again and conclude this event. Thanks a lot, Giulia, for a wonderful talk.
Thank you very much.
Yeah. So, yeah. I will stop the recording.